Welcome to the Essentials of Inorganic Chemistry. I am your friend Dr. Vidi Bhatt, presently discussing a chapter entitled Inorganic Polymers. This is the second talk in this series, and today I am going to discuss about silicones, also known as polysiloxanes. Here I will also discuss some industrially important compounds like high thermal silicones, silicone resins, silicone rubbers, oils and greases. On the thumbnail, I have shown structures of some important compounds involved in this silicones chemistry. You can see that the first structure is a linear polymer with alternating units of silicon and oxygen. Also, you can see that the silicon has two methyl groups attached over it. At the bottom, you will see one of the ingredients of the silicon polymers. This is your trimethylsilanol. In the second figure, your dimethylsilanol, and the third one is monomethylsilanol. I will be discussing the details about this later on. So let us formally begin the discussion on silicones. You will see here that I have written the word silicones in an unusual way because I wanted to draw your attention. See, the spelling of the element silicon is silicon, but when I say silicones, silicones, it means that I am talking about organosilicon polymers containing OSIO links, and they are named as silicones. These silicones can be broadly classified into three types: linear ones, cyclic, and then the cross-linked. First of all, we'll take a look at the preparations of different types of silicones. This preparation involves three steps. Let us discuss them one by one. The first step, you have to prepare an alkyl or aryl derivative of silicon tetrachloride. So you have to convert this starting material into monomethyl or dimethyl or trimethyl silicon chloride. Let us have a look at the different ways in which these compounds can be synthesized. The first one is, you take 2 moles of alkyl chloride, say methyl chloride, and silicon. You need a copper catalyst and high temperature of 300 degrees Celsius. In this case, you will get a mixture of products like methyl silicon chloride, dimethyl silicon chloride, and trimethyl silicon chloride. Another way of obtaining only one product is, take 2 moles of methyl chloride, silicon, and 2 moles of HCl, and again copper catalyst, 300 degrees Celsius is the temperature. You will get only one product, that is methyl silicon chloride along with H2 gas. So this is one of the ways of making methyl silicon halides. There is yet another method for making methyl silicon halides, and that is based on Grignard reactions. So, Grignard reactions involve RMgX. So in place of RMgX, we have Ca3MgCl. React it with SiCl4. You take 1 mole of RMgX and 1 mole of SiCl4, perform the Grignard process, and you will get methyl silicon chloride along with MgCl2. If you take 2 moles of methyl magnesium chloride, then you will get dimethyl silicon chloride. If you take 3 moles of methyl magnesium chloride, then you get trimethyl. So, in the first step, we have obtained methyl silicon chloride or alkyl silicon chloride. Now, in the second step, You have to convert the alkyl silicon halide into a group of compounds known as silanols. You know, in organic chemistry, when you use the suffix ols or ols, then you are talking about alcohols, and alcohols means OH groups. So here also silanols and silicon halides, they differ with respect to the halogen or the OH group. So let us see how this can be done. You can have, as we have seen in the previous reaction, you can have a variety of alkyl silicon chlorides. You can have methyl, dimethyl and trimethyl. So if you take methyl silicon chloride, react it with 3 moles of H2O, then upon hydrolysis you get methyl silicon trihydroxide or hydroxide, monomethyl silicon hydroxide, known as monomethyl silanol also, along with 3 molecules of HCl as the byproduct. If you take dimethyl silicon chloride, react it with 2 moles of water, then this hydrolysis will give you dimethyl silanol. In the same way, if you take trimethyl silicon chloride and react it with 1 molecule of water, then you will obtain trimethyl silanol along with HCl as the byproduct. So that is our second step. So first we prepared a silicon halide, or rather I would say alkyl or aryl silicon halide. Then in the second step we hydrolyzed it to obtain silanol. Then in the third step, a reaction known as condensation reaction has to be performed, which is about removal of water molecule, and upon removal of these water molecules we obtain the silicons, that is the polymers. Now let us have a look at the condensation reaction in case of different alkyl silanols. Now see, if you have monoalkyl silanols, then you cannot obtain polymers, you will get only dimers, because in this compound that we have prepared, methyl or alkyl silanol, if you are having trialkyl silanol, then the reactive site or the active site is only OH for condensation. So this compound can form only a dimer. Let us take a look in the picture, you will understand. You have 2 molecules of trialkyl silanol, the first one and the second one. Now condensation means removal of water molecule. So you have 2 OH groups. So say this H2O goes, then you will get this SiO-Si link along with release of 1 water molecule. But since you do not have OH group over here or here or here, there is no possibility of any of these 2 molecules to further react and extend the chain so as to make the polymer. What you can get at the most is a dimer. You can connect only 2 such molecules to obtain a dimer. Instead of this, if you have dialkyl silanols, then you can obtain 2 different types of polymers. You can obtain linear polymers, you can also obtain cyclic polymers. So let us take a look at this reaction. See, here what I have done is, I have taken 3 molecules of dialkyl silanol. This R can be CH3, it can sometimes be phenyl group also. That depends upon the application of the polymer. So now you have 3 molecules and each molecule is having 2 OH groups. So let us first consider a condensation reaction in which a linear polymer is formed. See, from this 2, H2O will go, and from here also you can remove H2O. So here you will have SiO-Si link, here also you will have SiO-Si link, and interestingly both the ends this one and this one, they have OH group. So they have a possibility of reacting with more molecules, more such molecules like R2SiOH twice, and the chain can be extended on both these sides. But on the paper, I do not need to show a very long structure, and I am sure you will understand. So I have taken only 3 molecules, and you can see that a trimer is formed, and this trimer is not an ordinary trimer. It is a trimer with 2 active sites. These are the 2 active sites. So this can further react with more dialkyl silanols to extend the chain, and you can obtain a very high molecular weight polymer, which is a linear polymer. Now, it is also possible that these 3 groups, these 3 molecules can form a cyclic trimer. See, the same things I have shown over here, R, R, Si, O and O. You are having dialkyl silanol. So, if this is called, repeating unit or the monomer, R2SiOH twice is your repeating unit or the monomer. Now, this can react with 2 different such molecules to form a cyclic compound, and once the cycle is closed, then you cannot have further polymerization. So here you can get only a cyclic trimer. Which compound you will get depends on the conditions of the reactions that you carry out. But in general, you will understand that if you have dialkyl silanol and you carry out the condensation, you can get 2 different types of products: linear trimer with a high molecular weight, or a this may not be essentially a trimer. It can be a tetramer, or it can be a polymer. But if it cyclizes, then you will get the cyclic trimer. So till now we have seen that if you have monoalkyl silanol, then what you can get is a dimer only. But if you condense the dialkyl silanols, then you can get linear polymers or cyclic trimer. Now let us see what happens when you have trialkyl silanols. These trialkyl silanols can give 2-dimensional cross-linked polymers. Let us see how it can give. So this time, in order to show cross-linking and 2 dimensions, I have taken 6 molecules of trialkyl silanol. Just take a look at one molecule. This is your one molecule. There are 3 OH groups on each of the molecule, and then there is R. The 4th position is occupied by R. Now friends, just for the sake of symmetry, I have shown almost all the molecules in same orientation. But you have to remember that sometimes it is possible that in place of OH you can have R, and in place of R you can have OH. So different possibilities of reaction will be opened up. But here if we consider that if they are symmetrically placed, then 6 molecules of this trialkyl silanol, when condensed or condensation polymerization is carried out, it will lose 7 molecules of water, and it can give this type of polymer. You see, this is a one of the orientations of a cross-linked polymer, and this is cyclic also. So cyclic doesn't necessarily mean that it is a 3-member. It can be cyclic, it can be high molecular weight, and it can be cross-linked. You can see that this polymer still contains 4 active sites: OH, 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 OH. So this can go on and on until a very high molecular weight is reached. So friends, these polysiloxanes or silicones can have molecular weight in millions. Now, in order to make this picture more clear, I am showing you some 3-dimensional structures. What we have seen in the 2-dimensional structures are, it appears that the silicon is square planar, but actually silicon is not square planar. Silicon, it belongs to carbon family. and it will undergo sp3 hybridization. So it will be tetrahedral, and therefore the actual structure of these molecules will be like this. You can see here, this is your monomethyl silanol, and this silicon is tetrahedral. Here also the silicon is tetrahedral in the dialkyl, and here also the silicon is tetrahedral. And because of this, a polymer, the picture that I am showing here is for a dimethyl silanol. So here you can see that silicon is not square planar, it is tetrahedral. The angles are 109.5. Therefore, the chains of this polymer will not be like a straight chain, even though we call it linear. Linear means that it is not closing, that's it. It's an open chain. And here I have shown you the active sites. This OH is your active site, and this OH is active site, which provides further opportunity for extension of the chain. Now, silicons are very important in industries. They have become very important because of their interesting physical and chemical properties. You will be surprised to know that these silicons are stable up to 300 degrees Celsius. They are chemically inert, they do not react very easily. Then they are found to be soluble in non-polar solvents. And the most interesting part is they have low viscosity even at low temperature. When we come to the application part, I will explain you the importance of this low viscosity at low temperature. Then they are hydrophobic. They do not get, they are water repellent, or they do not get wet by water. And they are insulators of electricity. And also they are non-toxic. So because of these general properties, the silicons find a very important place in the industries. Let us have a look at some of the general applications of your silicons. The silicons are generally used as lubricants, and silicons are superior lubricants because they retain their lubrication property even at high temperatures and low temperatures. Sometimes what happens that the lubricant that we use provides lubrication at room temperature, but if the operating temperature of the device is high, say it goes to 200 or 300, then the lubricant will lose the lubricant property, and therefore abrasion will take place, and therefore the appliance or the device that you are using will fail. But when you are using silicons, then you are sure that even if the temperature is around 300 degree or even in minus degrees, then also the silicons will provide efficient lubrication. Then I have mentioned that they are water repellent or hydrophobic. So silicons are used in making waterproof paper, waterproof clothes, and many other waterproof things. Silicons also find important application as insulating material for electrical motors and other electrical devices. Now, you have got a variety of applications of silicons. Depending on the applications, different silicons can be tailor-made, and the most popular silicons in the industries are classified as follows. First of all, high thermal silicons. Then you have silicon resins. Then you have silicon oils, also known as silicon fluids. And then you have silicon rubbers and silicon greases. So now we will take a look at all these types of silicons one by one. We begin with the high thermal silicons. The high thermal silicons are prepared by carrying out the hydrolysis of alkyl or aryl silicon halide in presence of aluminum or titanium compounds. So what happens that some of the positions of the silicons are occupied by aluminum or titanium. It will look probably like this. See, you have a linear silicon and say this position here you expected silicon, but because you have used aluminum during the polymerization, so one of the silicon is replaced by aluminum, and this replacement will result into high thermal stability of this silicon polymer. This is a linear polymer and it will it can be used even at temperatures around 350 degree. In case of cyclic polymer, one of the silicon can be replaced by aluminum in this way. You can have a look at the position of the cursor and you will understand. If you have titanium, then in place of silicon you can have titanium. Important thing to observe over here is aluminum is trivalent and therefore you don't have an R group over here, whereas titanium is tetravalent and therefore you will have the fourth position also over here. Now, it is worthwhile mentioning over here a silicon polymer having maximum thermal stability. This is called Brown's aryl silicon polymer, and here you will see that as such the polymer is same. It is a cyclic octamer, or rather 8 membered cycles are there, and a long chain polymer is there. In place of methyl group, here you have phenyl groups. So your cyclization, your cross linking and your phenyl groups, and finally the product is having very high thermal stability. So that was something about the high thermal silicons. Next I come to the silicon based resins. Now in polymer chemistry, resin is a term that is referred to material which is sticky and which is having very high viscosity. You know, viscosity is the measure of the friction between the layers of a liquid. If the friction is very high, that is the two layers cannot move, two adjacent layers or the upper layer cannot smoothly move over the lower layer, then I will say that the material is highly viscous. And generally this kind of characteristic is observed in low molecular weight polymers. Several organic based resins like vinyl resin, epoxy resin and acrylic resins are popularly used in industries. Sometimes silicons are blended with the organic resins to give silicon resins with desired properties. Now how to obtain these silicon resins? Dialkyl silicon halides. You have to take dialkyl silicon halides and you have to hydrolyze them in presence of monoalkyl silicon halides and then polymerize to give. Polymerize means you have to simply perform the hydrolysis or condensation reaction, and means then you have to polymerize it to give the silicon resins. Now these silicon resins, they are stable up to around 250 degrees Celsius, and by proper engineering or choosing proper constituents or introducing elements like aluminum and say titanium, you can increase the thermal stability of these resins up to around 500 degrees Celsius, and therefore these materials are used as electrical insulators. Silicon resins are used for coating, they are used for lamination, they are used as release resin to release two substances from each other. Then they are used in molds and electrical appliances. Sometimes they are mixed with paints, pigments and enamels so that the paints get a protection against heat and weather. Next we come to silicone oils or silicone fluids. Silicones which are designed in such a way that they contain a mixture of linear and cyclic polymers are called silicone oils. The dimethyl silicone oil can be prepared by hydrolyzing a mixture of dimethyl silicone halide and trimethyl silicone halide. The trimethyl silicone or the trimethyl groups occupy the ends of the chain and they prevent further polymerization. See, if you take a look at the reaction, you are having a trimethylsilanol and then your two molecules of dimethylsilanol and yet another molecule of trimethylsilanol. So on both the ends you have trimethylsilanols and you are performing the condensation polymerization, and what you obtain is a polymer where the ends are occupied by trimethylsilanols. Now because of this, the terminal groups will not have active sites. See, this terminal group has methyl, here also the terminal group is methyl, and therefore the extent of polymerization is controlled, and silicone oil of desired property is obtained. Some important characteristics of silicone oils: their viscosity does not change much with temperature. Then they are very good thermal insulators and electrical insulators. They have high thermal stability and they are non-volatile, that is, they do not evaporate easily. So because of these properties, the silicone oils are preferred in hydraulic fluids, dielectric fluids, high temperature oil baths, low temperature lubrication, and then oils for vacuum pumps. Here I have mentioned dielectric fluids. These are these fluids which are used for the purpose of preventing the fire or other accident due to static electric discharge. So this dielectric fluids can absorb the electric discharges. Because of their insulating properties, these silicone oils, they are very useful dielectric fluids. Next I come to the silicone rubbers. Rubbers are also known as elastomers. The dialkyl silicone halides are hydrolyzed and then polymerized to give silicone rubbers. For example, dialkyl polysiloxanes. I have already mentioned that the silicones are also known as polysiloxanes. Here, the presence of trialkyl and monoalkyl silicone halides results in two different phenomena. If you have trialkyl silicone halide, then as we have seen earlier, the further growth of the chain will be blocked. And if you have monoalkyl silicone halide, then you will see that large amount of cross-linking will happen in the polymer. An average molecular weight of around 1 million is desired in silicone polymers in order to obtain the properties which are expected from these rubbers or the elastomers. Now there is a process known as vulcanization. Vulcanization generally means cross-linking, which is a chemical process and is carried out in the rubbers using some peroxide initiators. If you have studied the free radical polymerization or free radical reactions, then we use peroxides in order to initiate the free radicals, in order to obtain the free radicals. And this free radical, say for you have CH3 group and you have used organic peroxide, then the CH3 group will be converted into CH3 radical, and therefore it can induce some kind of cross-linking in the polymers, and this cross-linking will result into the improvement of the tensile strength and other properties of the rubber. Tensile strength is the strength towards tension given to the rubber. Silicone rubbers have good elastic properties and they are oil resistant even at high temperature. Rubbers with thermal stability of about 200 hours at 400 degrees Celsius and 90 hours at 540 degrees Celsius have been prepared. These rubbers are used as electrical insulators for devices like transistors. They are also used as sealing the joints and seams of the aircraft. Then comes silicone greases. Grease is a semi-solid material which is generally used for lubrication to reduce the friction. So, silicone greases are prepared from methyl phenyl silicone oil. The oil is converted into grease by addition of materials like carbon black, then your dispersed silica and lithium soap of fatty acids, means lithium soaps of alkyls having 10, 12 or 14 carbon atoms. These silicone greases, they provide efficient lubrication in a very wide temperature range from -40 to 200 degree Celsius. So, the silicone greases, they find application as a lubricant of ball bearings operating at very high temperature as well as very high speeds, which are generally used in the different parts of aircrafts. So, this was something about these silicones, also known as polysiloxanes. I would like to end up this lecture over here and will meet you again. Till then, thank you and goodbye.